All right. Good morning, good afternoon, good day, good night, whatever day it is. For me, it's August. For you, it's probably October. Um, this is Miss Bowman coming at you, not live, but asynchronously. I'm here to go through the day one notes for our new unit. Now, we started that after the exam today. So I'm just going to go through in case you missed class so that you're able to kind of hear what I have to say. As per usual, I'm probably going to say, pause me, do the problem, unpause me. And a little bit of rotation. I'll probably mumble, go off topic a little bit because I'm here talking to myself in my office. But let's get your brain going a little bit. So we just finished unit one, our little unit on limits. So what are the differences between average rate of change, absolute change, and instantaneous rate of change? Now, two of those three we talked about last year, but average rate of change, absolute change, and instantaneous rate of change. So if you remember, you can go ahead, pause me, think it over. What do you know about AROC, IROC, and what we call absolute change? Okay. So take about 30 seconds, hit the little pause button, think about it, and then unpause me and I'll go over it. Okay, great. Now that you've had a chance to think about it, if you remember, average rate of change is the slope of the secant line. That's just the slope between 2 points on a given interval. It's how that function is changing for that given interval. Okay, instantaneous rate of change, if you remember that from last year, that's the idea that we're going to take the slope of a tangent line or the slope at one point by taking the slope between a point and a point really close to that and finding the slope from a point A to a point that's h spaces away from A, which is why it's called A plus h, and then limiting that h value to approach zero. So that was our IROC. Okay, and then absolute change, that is just the change in the height of the function or the change in the value of the function. So if I had a graph A and B, the absolute change would be the change in the height, not necessarily the change in the height over the change in the width, but just the change of the height of that function. So if I went from $2 and I ended with $11, that's an absolute change of $9. Okay, so it's just the length of that vertical line between the two functions. Okay, so today what I kind of want to do is on that, we're going to be talking about our second of three topics. Calculus is really just the study of three things: limits, derivatives, and integrals. And today we're going to introduce what the derivative is. So we're going to go through the definition of the derivative. Well, here is the spoiler. In 2.4, we define the slope of the curve to be this. That was the slope of any point, the slope of the tangent line, and that. So if you remember, again, I'm going to keep saying this over and over again because I really want you to understand where this definition comes from. Okay, but really it's saying I have a point A, and then I have a point that's h spaces away at A plus h, because A, move away h spaces would get us A plus h. I'm finding the slope, and then what I'm doing is I'm shrinking the distance between those two. So I find the slope between those 2 points, and then I shrink the distance so that the 2 points become one. So if you imagine, here's point A, here's point A plus h. Okay, and if this is the distance between them, all I'm doing is I am just taking this first point and moving it closer and closer and closer till it becomes the same as point A, so that there is no more difference between them. So that instantaneous rate of change is actually what we call the derivative of f at A. So this is the derivative of f at x equals A is the instantaneous rate of change of f of x at x equals A. So you already know the derivative, which is great. So let's do an example. Let's talk about notation. I totally forgot to mention that. Okay, so instead of saying IROC all the time or M of tangent all the time, we have notated the derivative or the rate of change of a function at a point with a lot of different ones, but the most common way to write the derivative is going to be using f prime notation. So we would write it as f with a little tick mark and then x, that we would read that as f prime of x, and that f prime, this means derivative. And when I say derivative, what am I talking about? I'm just talking about a little slope, that's all. Okay, so the derivative is just a fancy word for IROC. So when we talk about the derivative value, we're just talking about the IROC value, or the instantaneous range. So find the derivative value f prime of 2 for the function f of x equals x squared. So if I want to find the slope of this function at 2, which is what it's asking me to do, if I want to find f prime of 2, I'm going to find the IROC at 2. So I'm going to take the limit as h approaches 0 of f of 2 plus h minus f of 2 all over 2 plus h minus 2. And when you're doing the slope formula, you can write 2 plus h minus 2, or you can just know that those 2's are going to cancel out and it's going to be all over h every single time. So it really kind of doesn't matter. So now, to evaluate this, I'm still going to carry my limit because I'm not actually taking a limit until the very end. And I'm going to plug 2 plus h into my function. I'm going to plug 2 into my function and I subtract it, and then that's all over h. So if I take it another step, I don't know how I feel about this red pen, but I started, so I'm going to finish. I'm going to go ahead and distribute that 2 plus h out. Please don't tell me it's 4 plus h squared. It's definitely 4 plus 4h plus h squared minus 4 all over h. I can see here that my 4's are going to cancel. In fact, if my constants don't cancel, then I probably did something wrong. So then I have the limit as h goes to 0 of 4h plus h squared over h, which if I divide out an h is just the limit as h goes to 0 of 4 plus h. Technically, I should have this in parentheses since it looks like a sum. Then I'm actually going to take the limit here, so I'm going to plug in 0 for h. Now, again, at that point, when I replace h with 0, I've taken the limit. I can drop the limit notation, and I end up getting 4 as the limit value, which tells me f prime of 2 is equal to 4. So what that tells me is that the slope of this function, x squared, at x equals 2, so if I were to graph x squared and look at x equals 2, and I drew that tangent line, the slope of that line would be 4, okay? So that's what the derivative is. It's honestly nothing new. We're just calling it by a different name. Now, all great mathematicians look for patterns. All great mathematicians look for efficiency. Okay, this process of using the difference quotient to find the slope at a point is one way that you do it. And it's probably going to be the way that you're most comfortable with because we did so many difference quotients last year. Okay, but there is another way to find the slope at a point, another way to find the derivative at a point. So we're going to see where that comes from. Okay, so I'm going to explain where it comes from, and then I'll show you how to use this definition. So the alternative definition of the derivative. In the first example, if I just go back a little bit, if you remember, the logic behind this was that I took a point A that I wanted a slope at, I found a random point h spaces away from A, and then I made that second point move closer and closer and closer until there was no space between the 2 points. Okay, so that's the idea of the first one. It's describing everything in terms of the distance between the points. The second way is the idea is that we're going to start with 2 points, the one we want the slope of, and another point that I'm going to keep general. So here we're going to take 2 points, the given point, and a general point. Okay, so I have the point A, comma, f of A, and a general point, which would be in terms of x. So a general point on the function would be like any x, comma, f of x. And I'm just using f of x instead of y here just to have function notation. So the idea is this is the point we want the slope of, and this is any other point on the function that I'm not going to define. Okay, so I need to make myself have a little more room here. And what I'm going to do is I'm going to find the slope between those 2 points. So I have my point A and another point x. Okay. So the slope between those points would be f of x minus f of a over x minus a. Now, in order to get it to be instantaneous, what we want is we want this really to be the slope between a point and itself. Now, in the first definition, we described moving this point and describing what's happening to the distance between them. So in the first the first definition, the difference we called h, and we just kept moving it closer until there was no distance between the points. In the second definition, instead of describing it as a distance, we're going to describe it by this point. We're going to say, okay, we want this point to move closer and closer and closer until it becomes the point we want. So the second point is going to become the first point. And so what we're going to do is we're going to limit the x, which was the random second point, to approach the value of the first point. So instead of saying like 2 and 2 plus h, we're just going to say I have a point at 2 and I have a point at x. And eventually I want that x value to become 2 so that it moves closer and closer and closer until it approaches the same point. So again, a little visual. I just take this point and I'm just moving it till it becomes the first point, and then I have a slope between a point and itself. So we're going to use the same example just for the sake of knowing what the answer should be. And we're going to use the second definition. Now, if I say find the derivative value, I don't care what definition you're going to use, but you need to be familiar with both of them. So the second definition, again, is just the slope between a point and a random point. And we're limiting the second point to become the first point, and that is also the derivative value at a. So if I wanted to do that, my first point would be 2 and f of 2. My second point is going to be x and f of x, which f of x is just x squared, so I'm going to write it as x squared. And actually, f of 2, if I plug in 2, is 4, so let's just make it easier. The first point is 2 comma 4. The second point is x comma x squared, because again, x squared is the function, so I'm just putting it as x squared. So then f prime of 2 is going to be the limit as x approaches 2. So that's the first part. The limit isn't x approaching 0. It is the second point is approaching the first point. So the x is approaching 2, and then I find the slope expression between these 2 points. So x squared minus 4 over x minus 2. So now I have a problem that just looks a little easier than the difference quotient. But if we look at it and I try to plug in 2, I'm going to end up with 4 minus 4 over 2 minus 2, which is 0 over 0. So when we deal with this, we're going to actually have an indeterminate. So what I'm going to do is I'm just going to take this expression and simplify it. So if I factor my numerator out, I can see that I have an x minus 2 that cancels. So I end up with the limit as x approaches 2 of x plus 2, my simplified expression. Now I'm going to take the limit. So everywhere I see x, I'm going to replace it with 2, which gives me 4. So that tells me f prime of 2 is equal to 4. So you can see the slope is the same, which makes sense. It's the same point, the same function. Everything should end up with the same answer. It's just a different way. So method 1, take a point at 2 and a point h spaces away from 2, find the slope, and then limit the space to approach 0. The second definition says, here's your point at 2. Here's a random second point that I'm not going to define, but then I'm going to limit the second point to become the first point. So definition 2, there's an x here. Definition 1, there's an h here. Okay, so it's very different and easy to get confused. So just so you know, that would be the best. Okay. So on that note, let's continue on. I think my computer is tweaking out. Oh, it's still recording. Great. I'm going to have to edit this out in a second. All right. So let's talk about some food for thought. So let's just talk about the derivative. So the derivative is the slope. So we're just going to be investigating some ideas about slope. So the first one I want you to think about is the derivative of y equals sine of x at x equals pi positive or negative? How do you know? So is the derivative, so you have to think, what does the derivative mean? It's the IROC or the slope. Is the slope of y equals sine x at x equals pi positive or negative? And how do you know? So pause me, think for 30 seconds to a minute, and then unpause me. Okay, welcome back. I'm going to laugh when you guys don't pause me, and then I just sound like I'm a fool, but hopefully you're pausing me because I'm telling you to, and it wouldn't do you any good not to try it on your own first. Okay, so if I graph my little sine graph, which is just a little good review of Math 4, I have this graph right here. I know this is pi over 2, 3 pi over 2, and 2 pi because that's one rotation of the unit circle. Okay, so the question is the derivative of y equals sine of x at x equals pi positive or negative? So if I look at x equals pi, is the derivative positive or negative? And I'm going to say negative because f of x, well, I guess it's y, because y equals sine of x is decreasing. So if you notice here, since the function is decreasing, it has a negative slope, and slope is the derivative, so it has a negative derivative value. Okay, let's try another one. So I want you to try this one. Label points A, B, C, D, E, and F on the graph below. So point A is a point on the curve where the derivative is negative, B, where the value of the function is negative, C, where the derivative is the greatest, D, where the derivative is 0, E and F are points on the curve where the derivative is about the same. So pause me, think about it for a while, maybe 2 minutes, unpause me, and we'll go over it. So I'll let you pause. Okay, welcome back. So with this one, you can have many different answers, but I'm going to put my point A right here. Anywhere where the function is decreasing would be appropriate for A. Point B, where the value of the function is negative, that would be down here where it's below the x-axis, so anywhere down there. Point C, a point where the derivative is the greatest. So I'm trying to find where the slope is the greatest. That's not going to be the maximum of this graph. If I'm talking about where the slope is the greatest, I'm going to be looking at where the slope is the steepest. And it looks like it's the steepest maybe right here. So I'm going to put C right there. Okay, D is where the derivative is 0. So that would be anywhere it levels off. I could put D here, I could put D here, or I can put D here. And then E and F where the derivative are about the same. Now you could be slick and just call this E and F. Okay, I could also maybe do like here and here. Anywhere where I think the tangent lines would be parallel would be derivatives being the same. Okay, number 5. Let's see, for the graph below, which of the following is greater in each of these? So pause me, answer each of these, give you maybe 30 seconds, 45 seconds. Actually, you can pause me for as long as you want because you're doing this on your own, but unpause me when you're ready and I'll go over it. Okay, so in each of the following, which is the greater in the following pairs? Average rate of change between 1 and 3, and I need to mark this on my graph for me to see it. So 1 and 3 would be here, and 3 and 5 would be here. I can see the average rate of change between 1 and 3 is greater because it has a steeper secant line. Okay, f of 2 or f of 5 because it has a higher value. So remember, f is just the function's value. F prime is the slope. So the slope at 1 or the slope at 4, the slope at 1 is greater because the function is steeper at x equals 1. Okay, we'll do a couple more just to keep our brains getting comfortable with the derivative. Okay, so what we're going to do here is we're just going to label. Again, we're just going to kind of draw. So On your own, try these. It'll probably take you 2 to 3 just to kind of get through them. 2 to 3 minutes, that is. Note, for some of these, you're going to be marking on the graph. For some of them, you're going to be estimating them. Okay, and some of these require more than just plotting a point. Feel free to write a word or phrase next to each on the grid. Okay, so f of -1. F of -1 is here. It's just the point. Okay. F of 5 minus f of 4. F of 5 is here. F of 4 is here. So f of 5 minus f of 4, this would be B. So here's, or sorry, C, because I went down instead of over. Okay, so that's the absolute change. That's the length of that vertical line between these two heights. Okay, if I go back to B, f of 2 and f of 4, that would be the slope of that secant line. So this is the A rock. Okay, so I'm just going to put a little m so I know I'm talking about the slope there. D, f prime of 2. F prime of 2 would be the slope at 2. That's going to be the slope of the tangent line. So this is the I rock or tangent slope. Okay, f of 4 minus f of 0. Now we're getting into some repeats. F of 4, f of 0. That would be an A rock. F, so this is my E. I guess I should be marking this. This is my D. This is part B. F of 3 is that point. That's F. F prime of 0.2 would be about here. That's going to be G. So that's like the tangent slope or the I rock. Now, this one is interesting. The limit as h goes to 0 of f of 4 plus h minus f of 4 all over h. Spoiler, that's just the definition of the derivative. That is the same thing as saying f prime of 4. So that would be h. It would just be the slope of the tangent line at 4. Okay, we'll try one more, and then we'll call it a day. So this last one, we're going to sketch a graph with the following features. So pause me. Take about 2 to 5 minutes, depending on your speed. Try this question. You're going to graph a function, make it continuous. Okay, graph a continuous function that has these characteristics, and then I'm going to go through my graph as well. Okay, welcome back. Can't wait to see what your graphs are in my head. I imagine they're all perfect because I'll never see your notes. That's great. Here we go. So my advice to you is when you're graphing is graph the key parts of the information that you can get right away. Points are my go-tos, okay? Points and asymptotes. So I know f of 5 is 2, that's a point. F of 0 is 3, that's a point. I also know the limit as x approaches infinity. That means this is a horizontal asymptote is 4. So as I go towards infinity, the height is going to be approaching 4. So I'm just going to kind of make an arrow that goes horizontal at a height of 4. Doesn't matter if it's above it or below it, just as long as it looks level with it. Okay, let's see what else we know. F prime of 3 is 0. So now I'm going to make some notes over here because I can see all of the rest of these has to do with slopes. So now that I have kind of like my skeleton, I'm going to write some notes. So f prime of 3 is a 0 slope. So I know f prime of 3 is flat. F prime of 2 is negative, so here we have a negative slope, and f prime of 7 is a negative slope. So wherever I'm at 7, I have to be decreasing. So I need to be decreasing somewhere. Now, because this point is here, I mean, I guess I could decrease that way, but then I got to make sure I come up and go that way. Your other option is to increase and then turn around. Okay, so either one of those would have been fine. Here I'm just going to flatten it out right there. It doesn't matter what height you do it as long as you're flattening it out because we don't know what's happening between here. And then here I'm going to be negative, so I'm just going to kind of make it like that. So there's my function. Again, I'm just going to erase one of these two because it doesn't make sense to have both of them. So let's just erase this one and I'll keep that one. But again, lots of different answers, but what I'm going to be looking for is, do you have a negative? Ooh, let me try that again, folks. Okay, so do you have a negative slope at 2? Do you have a 0 slope? Do you have a negative slope? Do you have this, this, and this? Okay, you've sketched some graphs last year, so you should be pretty comfortable with it. But that is the derivative, guys. So try it. Hope you Let me know if you have any questions. Come to office hours, email me, and I'll see you soon.